Let's start the class. Hello. You want to sit close to me now? All right, let's start the lecture. So, all right, attention, attention. So we are enter the fourth lectures, and we already cover 5 chapters. Those 5 chapters that we presented here are considered as review background information. So from this point onward, we get into something new. So this chapter is about inference line. It's a very important concept that you should know. And we are going to confine our discussions on the determinate structures only, statically determinate. For indeterminate structures, the behavior and the analysis will be slightly different. So you should know that the determinate structure, of course, are referring to those structures that can be analyzed purely based on equilibrium conditions. May not necessarily means that it only has 3 reaction forces. It's actually depending on whether you can find the extra constraints or equations to help you. But those constraint equations will be also coming from the equilibrium conditions. Okay, so let's start. So why inference line? What is inference line anyway? Why do we want to study inference line? Now, previously, we studied shear force bending moment diagrams. Hello? So we studied shear force bending moment diagrams. So you know exactly how to obtain those. So what are shear force bending moment diagrams? So those shear force bending moment diagrams are internal forces inside the structure plotted against a set of fixed external force. So this is what happens when you do a shear force bending moment diagrams analysis. You have a set of forces that include concentrate force, distribute force. Very quickly, please sit down, because you'll be lost very quickly in a few minutes. So we have a set of given external force getting to the structures, and because of those forces, you will have internal forces developed, and these internal forces will be changing respect to the locations. So different locations should have different internal forces. And then we can plot them and then get the shear force bending moment diagrams, and hopefully we can use that for design. But unfortunately, that hope is not realistic. It's not sufficient. Because basically, we know from the first chapter, the structure will be designing against not dead loads, which is kind of fixed. Patterns, loading, they're kind of fixed. But they are also designed against live loads. So we need to consider live load as well in our design and analysis. So what is live load? Live load. Now, this is dead load. Dead load is kind of imposed, never changed, magnitude distributions, kind of fixed. But live load is different. Live load can change location. You probably can estimate the magnitude of the live load based on the functionality of the structures. But the locations, you need to make it flexible. So for instance, like we have the class here. So 150 of you come in. This is live load. And after the class dismissed, you go out. So load removed. So this kind of dependency is called life load. So concentrate life load can change in locations. Also, distribute life load can change not only in location, but also in the regions. So for instance, distributed life load can be here, can be there, and can be coming in with different sizes, acting at different regions. So that imposes a great difficulty in our design. All right? The loadings kind of sort of dependence, time-wise or random-wise. So our mission is, if I give you a set of dead loads and kind of life load, which can change or vary at locations. So the issue here is, can you give me the maximum shear force and maximum bending moment that were developed inside the structures so that I can use them to design the components? So that's the issue that we have to handle. Basically, the issue is coming from the life load that can change locations and regions. Please. This chapter, the very important thing is the concept. Eventually, you will be confused completely, and the confusion is actually coming from the first few minutes of the lectures. If you don't make it clear, you'll be very, very confused later on. Hey, gentlemen at the back. Okay, can my bridge survive? So you're designing a bridge, but you'll be handling some sort of very strange life load. They come in, they act on different locations, and maybe it's a big truck, and maybe it's a small truck, or maybe it's a big dinosaur coming in, and can my bridge survive? That's the issue that we need to address in this chapter. All right, so what is inference line? So inference line concept goes like this. I'm trying to handle some sort of traveling loads or time-varying loads. So I want to study what is the relationship between a force and the locations of the loads. Right? So again, I want to study what is the relationship between one force and the locations of a traveling load. So for instance, I select that force and then let the force travel across the structures and determine what is the variations of that force. So that's called inference line. So inference line has been used quite commonly, especially for highway bridges, highway structures. So for highway structures, very important critical highway structures, long span, after their completions, most of the time the owner, sometimes, owner usually is government. Government will instruct the builder, the constructor, to perform the so-called load test. So there are several kinds of load tests. So one of the load tests that most of the time contractor have to do is the inference line load test. So what they need to do is they need to have some very heavy truck, heavily loaded, and then ask the truck to be positioned at different locations of the bridge. So this is kind of a test that you will commonly see for very critical, very important highway structures after their completion. So like we have this bridge, Kopstreamen Bridge, and Qingma Bridge, Dingao Bridge. Now all of them have been gone through this kind of inference line test after their completion. So this is a photo taken during the inference line tests. So this is a very, very heavy truck, and then they are positioned at various locations on the bridge. And of course, if you want to measure the forces or internal forces inside the bridge, you need some sort of sensor. So these are the sensor cables and computers acquiring data. So this is a domain that you don't normally see in universities. We are only doing analysis, but in practice, you will need to do this sort of measurements which correspond with your analysis. Okay, so inference line. So make a comparison between shear force diagram, moment diagrams, and inference line. Now, they are very similar in appearance, but carry totally different meanings. So that's the first thing that you need to be aware of. If you are late, I bet you will be lost already. You guys. 5 minutes, 10 minutes late, you will be lost, I bet. All right, so what is shear force and bending moment diagram? Here, I have a fixed loading, fixed locations, fixed magnitude. Everything is fixed. Loading is fixed. And I plot the internal shear force bending moment diagrams at different locations. So I should have X and V, X and M. So this X is the locations where you plot the shear force bending moment diagrams. I might seriously consider asking to stand behind the row. Next time, you're disturbing. Okay, so that's shear force bending moment diagram. So what is inference line? Inference line is defined. This is shear force bending moment diagrams. What is inference line? Inference line, first of all, you need to choose one force. This force can be reaction, can be internal shear force, internal bending moment. But anyway, you need to choose or fix one force. And then you plot the magnitude of that force with respect to the locations of a traveling force. So here, this applied force, downward force, is traveling across the structures. So at different locations, because of the locations of the force, the equilibrium will tell you that the forces will be different because the locations of the loading is different. So you analyze, you move the loading across the structures, obtaining all this corresponding shear force or bending moments, and then plot them against the locations of the loading. Then you have the so-called inference line. So they are quite different concepts, although eventually they look very similar. Okay? So that's something that you have to be careful about. So a lot of people having difficulty drawing inference line is because they basically do not understand the definitions of inference line, and they got confused with the shear force bending moment diagrams. Okay, so again, let me repeat. Shear force bending moment diagram that you know from your previous courses, they are shear force distributions corresponding to a fixed loading. On the other hand, inference line is you need to select one force. This force can be internal shear force, internal bending moment, or reaction force. But you need to select one first. And you will be plotting the magnitude of that force with respect to the locations of the downward external force. Okay? So x carry different meanings. The x coordinate carry different meanings. All right, so here is the definitions of the inference line. So inference line is a graph of response functions, such as reactions of internal forces of a structure, as a functions of the positions of a downward unit force moving across the structures. All right. So it's non-dimensionalized with respect to the magnitude of the external force. So that's why we make it downward unit force. So it looks like this. x-axis is the locations of the downward unit force. Y-axis is the response that you choose. The response can be reaction, can be internal shear force, or internal bending moment. So any force, you can choose one, and then you just plot it against the locations of the downward unit force. Okay, so that's definitions. Now, there are basically three ways to obtain or construct inference line. So the first one is point-by-point calculations, which is basically follow the definitions of the inference line. So it's just relocating the external downward unit force at different locations, obtain the reaction or obtain the response that you are looking for, and then plot them against the locations of the force. So that's called point-by-point calculations. Follow definitions. The second approach is called inference line equations. So instead of doing point-by-point calculations, you make the loading, locations of loading x, and then you just perform equilibriums. Hey, don't play phone. As I say, I don't have a mandatory attendance requirements. If you don't want to listen, if you want to sleep, like that person there, please go out to sleep. Wake him up. If you want to sleep, go to the library. Library. Yeah, as I say, no mandatory requirements for you to come here. You know, if you want to play your smartphone, go to the coffee shop. Right? So when you're here to learn. All right? Because whatever you do, you'll be affecting your friends sitting next to you, which is kind of troublesome. All right. So we'll go through these methods in this chapter. The methods of the highlight of the methods is this graphical approach. That is a very convenient and very efficient way to construct inference line. So I will hit on this more. All right? But first, let me go through this definition approach, which is kind of straightforward. You just follow definitions, and it ends up with calculating a lot of equilibriums. All right, so let's see. I have a simply supported beam, A and B. Length is 10 meters. So I want to construct inference line for AY, which is a reaction force at A. So by that, I mean that if I have a downward unit force, magnitude is equal to 1. Dimensions, unspecified. Could be kilonewton, could be newton. Non-specified. So just downward unit force there at any locations of the structures. And I want to plot the magnitude of the force, AY, as a function of this x. So I go through a bunch of calculations. I can place the downward unit force, firstly, at location A, directly on top of A. Then I know AY is equal to 1. Right? You don't need a very sophisticated equilibrium to answer that. If I position my downward unit force at A, then AY is equal to 1. Now, if I move my force to this location, 2.5, then I can analyze this, obtain AY using equilibriums. So equilibrium analysis tells me that AY should be 0.75. So next, I move the load to the midspan, and then go through the equilibrium calculation again. AY is equal to 0.5. OK, so I table them. So when the locations of the force is at 0, x equal to 0, AY is equal to 1, x equal to 2.5, then AY is equal to 0.75. So you have a bunch of values obtained from equilibrium calculations. And then next, you just plot them out. So it's a very straightforward definition-based approach to construct inference line. So each one of these points represent one equilibrium calculations. So no problem, right? No problem. So if I ask you to do a By, vertical reaction force at B, inference line. Can you do that? Yeah, of course. Just calculate By instead of Ay using equilibriums. So you should have another table, and then you should have another line for By. All right, any questions up to now? This is by definitions, which is kind of straightforward, but kind of tedious, right? Tedious. Okay, now the second approach is by inference line function, by functions approach. Now, instead of just doing point-by-point calculations, now, if you are very quick, then you say that, all right, so algebra is for that purpose. All I need to do is just assume the locations of force as an unknown x. X change from 0 to length, L. So all I need to do is just specify an unknown variable x there, and that x goes from 0 to 10. And then just do one equilibrium analysis. Then you can anticipate that Ay will be functions of x, right? You just come over here, take moment equilibriums. Then you can find Ay as a functions of x. So here. All right, so what is that x? X is the locations of the downward unit force. So this x is allowed to move from 0 to 10. So, great. So this functions turns out to be the inference line for Ay. So plot it out exactly identical to the previous approach. You do point-by-point calculations. Of course, immediately you see, instead of doing a bunch of equilibrium calculations, now I only need to do one-time calculations. So more efficient, right? More efficient. So we noted that the inference line that we obtained in this particular example, indicating that it should be a linear functions of x. X is the locations of downward unit force. So if you do moment equilibriums, then you see that inference line is going to be a linear functions of x. Linear functions of x. Okay, so the conclusions, after some examples, I'll show you later on, that all statically determined structures have inference line that consists of straight line segments. So they can have different form, but they are always consist of straight line segments.